Trevor arrived at the University of Waterloo in 1974 and spent the next 40 years as a student, research associate, adjunct lecturer, and technical staff member. As a member of the Computer Systems Group from 76 to 94, he participated in many development projects, from programming language compilers for the IBM mainframe to operating system and programming language development for mini-computers and first-generation desktops. Following a 10-year sojourn in the private sector as a tech entrepreneur, in quotes, Trevor returned to the university in 2004, joining the staff at CSCF. While there, he was involved in all aspects of CSCF's activities, including research support, infrastructure, and network management, and as the technical manager of the user support group. Since retirement in 2014, Trevor's been active in the University of Waterloo Computer Museum. Now, the bio he provided, I think I would be doing you a disservice if I didn't also mention that Trevor, as many of you will know, is president of the Staff Association for a number of years, starting in 2010, and that in 2015, he received the honorary member of the university, which is the highest honor a staff member can receive at the University of Waterloo. So let's hand the floor over to Trevor.
So thank you for inviting me to give you an opportunity to show off. This isn't my hardware anymore. This sat in my basement for 30 or so years until my wife finally said, you know, we got to do something with that. So I donated it to the museum along with, at last count, some 600 other artifacts, including a stack of business cards from the 1980s that you can probably throw away, I think. I don't think we need those anymore. So what I'm here to talk about today is the development, the rationale behind the development of this thing. I'll turn this around so you can see it from the front. This is what we would refer to as the Commodore SuperPET. It was a piece of hardware that was designed, prototyped, not manufactured, here at the Computer Systems Group, 1980 through 82, let's say. Its development led to the development of another gizmo, this thing, which we would call a Microwatt. As we'll discuss, the innards of this thing and this thing are essentially the same. We'll put those in context in a minute or two. So, turn this around. Oh, before I turn it around, I'll show you. This is the way we build hardware in these days. This comes with a lid, of course, that you can tip up so that you can see the inside. Comes with a little prop rod, just like the hood on your car, and part of that is the original thing that Commodore built and made. The other part of that is the thing that we designed and had added in to turn it from a PET into a SuperPET.
Need a new copyright?
All right. And we'll turn this on, and you know, if all goes well and Murphy doesn't rule, we'll actually have a demo in a minute or two. Actually, I'll turn it on now so that it can get warmed up. You know, these tubes, they take a while to warm up. So, I'll preface my remarks by saying I'm speaking not as a faculty member, not as a historian, but as a software developer who worked on the development of this device. At the time, I was a junior staff member, fresh out of school. So, you know, I have a certain perspective on what we were doing and how things worked out, and certain people here probably know a lot more about it than I do, but so I hope I don't, you know, cause too much consternation in the things that I say. So we'll start out asking the question, how did we get from a punch card? Both Eric and Scott have spoken about, you know, the way computing was with the 360 and student computing, all card-based, card and you know, printout-based. How did we get from that to this, to a desktop microcomputer based system used for student computing, and indeed from that to the Microwatt, which was the thing I showed you before. You notice that this is serial number 15. This was built by a spin-off actually from the Computer Systems group, a fellow by the name of Jerry Christ, who left our group to go and form a company called Northern Digital, which is actually still around today. It's called NDI, which is Northern Digital Inc. But this was their first gig, was to build microwatts to be used at the university. So, as we have heard, in the before desktop, before microcomputer era, we had cafeteria, what was called cafeteria style computing, which was either famous or infamous, depending on your perspective. You punched up, your little deck of cards, you go stood in a line, you handed them to somebody, and if you were lucky, you walked around the end of the, the counter, and by the time you got there, your job was done. The principal programming languages that were used, certainly from the computer science perspective, there were two of them, because, why would you need more than two? There was Fortran and there was COBOL. And that's what were used in the first and second year courses. There were other things as well, but those consumed the bulk of the sort of first and second year computer science programming languages. So the interesting thing about punch cards and printouts is that they're paper. We used to refer to cards as wholly blocks of wood, thin blocks of wood when they were full of holes. They cost money. And indeed, they were viewed as consumables to the computing process. And Wes Graham, who was a faculty member but had spent 10, 12 years, 15 years as the director of the computing center, came out of his budget to buy all these punch cards and the paper that ran through the printers. And when this would be sort of 1973, 1974 kind of time frame we're looking at, just after I got here. And he kind of said, we're spending an awful lot of money on punch cards and printouts, and shouldn't we be finding a way to cut that budget back? And it was observed that you could buy a PDP 1145 every year for the amount of money that we were spending on consumables. Interesting anecdote, I visited the University of Hawaii in 1981, where they were still using punch cards and printouts for their undergrad computing. And the way they solved the consumables cost problem was they converted one of those, like in the hallway out here, one of those vending machines where you stick in, 4 quarters and you press a button and you get a, can of pop or a, chocolate bar or something out of it. Well, they put punch cards in the machine. You get a little deck of 100 cards. You pumped in 4 quarters, $1, so a penny a card. And that's, I guess that taught the students there to be very accurate in their typing, because they were actually paying for the cards themselves. We never did that here. The solution we came up with here was to say, well, the IBM 36075, which was the batch processing system at the time, it could handle a lot of stuff. So why don't we take, PDP-11s were around, they had interactive capabilities. Why don't we try and find some way to use a PDP-11 to sort of act as a front end to this batch engine that ran on the 36075. And so people will sit at it, they'll type their little programs, and then when they want to run their program, they'll say run. It'll get sent off to the 36075, it'll get run, and the output will get sent back, and they can look at it. And so basically it was designed to do 2 things. One, to eliminate the consumables that were embedded in that process, and 2, to make it slightly more convenient for people. They didn't have to stand up and go and walk to a counter, and they could sit in their chair the whole time. So to that end, we developed something called the Waterloo Interactive Debug Job Entry Terminal, better known as Widget. And so by 1976, we had, it says hundreds of these. That's a Volker Craig terminal, if not hundreds, many dozens anyway. And that's where people did their computing. As courses converted, they start using Widget. Now, Widget met with, what's the right word? Middling success, shall we say. In fact, it was so middling that it was memorialized with T-shirts I was working at the time for the School of Computer Science. Well, in fact, in those days, I think it was probably called Applied Analysis in Computer Science, as what we would now call today an ISA. In those days, we called ourselves tutors. And the course that I taught, of course, used COBOL, or of course that I TA'd used COBOL, so that the obverse of the widget sucks t-shirt was the natural COBOL sucks t-shirt. So, you know, widget, you know, it did its thing. It saved budget on cards and paper, and it worked. It had its problems.
So what was the downside of widget? Why did it suck?
As it turned out, this process of submitting from the interactive terminal to the batch somehow wasn't as efficient as it needed to be. When you submitted your job, you would be told what queue position you were in to access the batch processor. And, you know, the first couple of terms we used that you'd be, you know, the queues would be 2 or 3 or 4 elements long. And then by the time it became very successful, they'd be 40 or 50 long. And the sad thing was you would expect the queue, your queue position to decrease. Preferably in a monotone decreasing sequence. However, it went the other way around. You'd be submitted at queue position 40, and then you discover 5 minutes later you're at queue position 50. I can't speak. I wasn't involved with the development of widget. Maybe Don can speak to it. I don't understand why that was true. Whether it was a scheduling, whether it was a priority problem, I don't know.
To make it worse, it was particularly bad at the start of every period and at the end of every period. When students just arrived, just had to leave for the process. So it became like, it couldn't handle peak loads at all. I think that was...
Yeah, I mean...
With the peak load problem together, that made it an impossible system for the students to use. Peak loading was a big issue.
I'm sorry?
Peak loading was...
Yeah, okay, so the comment is that peak loading was a problem. It didn't meet with tremendous student approval, let's put it that way. So, this was 1976, 1977. It's about this time in the history of computing that the first microcomputers are showing up, the Apple IIs and the TRS-80s of the world. So we thought, well, you know, this is something we should sort of understand. So we bought a couple of them. And we bought the very first version of one of these was a sort of a skinny little monitor. It had a little cassette tape recorder embedded in the keyboard, and it had a horrible little keyboard, 40-column PET. And the first thing that we noticed was if you actually wanted to do any serious programming on it, you had a one choice, BASIC. And the particular version of BASIC that it used was especially horrible. We saw a picture of Edsger Dijkstra earlier, and one of his other famous quotes, besides, you know, the fact that computing has nothing to do, computer science has nothing to do with computers, is he wrote a seminal paper in 1968. The go-to statement considered harmful. Go-to considered harmful. It's a fascinating paper. I reread it just the other day. It's 3 pages long. And yet it had a profound influence on the industry. The kind of BASIC that was available at the time was really horrible. So the first thing we said was, well, can we make a better version of the BASIC? And so that was the task we set to ourselves, was to take the BASIC that was there and sort of make it better. We did that. That was happening in January through April 1980. In 1980, we made it available, and the way we made it available was we burned it into a little chip. This computer actually has one. I can demo that at the end. Burned it onto a little chip, stuck the chip in the machine, did some magic incantation, and suddenly the version of BASIC that you had got better. So that was a way for us to get our feet wet with desktop computers, the PET. You know, taking a step back, we said, well, what is it you know, if we want to use these things for real in teaching first and second year computer science, what is it we need them to do? Well, let's recognize some of the basic requirements. First of all, as Scott mentioned, I think, these are entry-level applications that the students are writing. They get a weekly assignment to write a bunch of programs. The first rule is as soon as you get the program working, it's done, you go on to the next program. Runtime performance was not an issue. The development process was what was important. How fast could you compile? You didn't want to wait 30 minutes to compile a 10-line Fortran program. Getting a Fortran program compiled in 5 seconds would be more what you wanted to do. The cost in those days was such that, we taught some hardware courses, assembler language programming. We certainly couldn't afford to have students using real computers in those days. So we used to teach us hardware and machine language programming using batch simulators, using either a widget as the front end to the batch or people standing in lines to submit cards. I should note that there were specialized resources available in computer science for teaching 3rd and 4th year courses, the Honeywell TSS that we spoke about. There were some PDP-11 Unixes around. There was one on the 6th floor. We did have an IBM VM installation. The resources there were limited. They couldn't handle, when I was a tutor for the first year computer science course, we had 800 to 900 people in a course. We certainly couldn't afford to put 800 or 900 people on the Honeywell in those days to teach first year courses. So the first and second year courses were still using the IBM 360 and batch, and it was the upper year courses that used the specialized resources. So we knew we wanted to use desktop systems, but how are we going to do that? Well, we looked at what was available, 1980, 1981. That's before the IBM PC existed. There were Apple computers, there was the TRS. We looked at those very seriously, and they just really weren't going to cut it. You couldn't put the programming languages that were required onto them. Could you develop them? Not really. Both of those systems used what were referred to in those days as 8-bit CPUs. An 8-bit CPU now would be, what you'd put inside a $50 microwave oven. They were not particularly well suited to doing advanced software development, which is what we were going to need to do. They were expensive. They didn't have networking. Well, there was no networking in those days. Not much, anyway. Things like the Apple didn't come with a monitor. You had to buy a TV to go with it. They just really didn't work out. Neither of them had floating point, so you couldn't really do arithmetic. So we were kind of stuck. We knew we needed to figure out how to put a computer in front of each person, but we didn't know what to use. Now, one of the observations we made was we were not in the same business as what the Apple IIs and the TRS-80s of the world were in. Those were systems designed for hobbyists, for enthusiasts to have at their home and play with. The standard was 4K bytes of memory. They had cassette tapes, or if you were really fancy, they had floppy disks, 5¼ floppy disks for storage. We couldn't imagine, 800 people issuing them all a couple of floppy disks and expecting them not to lose them by the end of the second week of classes. So we had to have a centralized storage mechanism where, a student could walk into a lab, use a computer, save their files someplace. Today we call it the cloud. And then tomorrow they'd come back, use a different computer, they could retrieve their files from the cloud. This was radical thinking in those days. In those days, you had a computer, you had a cassette tape, what more did you want? We realized that was not going to work in the sort of institutional setting that we had. So as a little aside, we've been playing around with PETs and other things, and we were looking at taking a Motorola, which was a 6801, which was sort of a little bit fancier than the CPU that was inside these things, and trying to do things with it. And in one of those, serendipitous moments, a co-op student whose name I wish I could remember, but I can't, was looking at 6809, Motorola 6809 processor, which was once again a related product. A little bit fancier, was a so-called 16-bit, pseudo 16-bit processor, much more powerful, much more adapt to building software. And he noticed that the pinout, the pinout is the arrangement of what the pins on the edge of the CPU do. He noticed that the pinout on a 6809 was almost the same as the pinout on a 6502, which was the CPU that was inside these things. So we thought, well, a really cheap way for us to build a more advanced microcomputer was we'd take one of these things, we'd pop the lid open, we'd pry the 6502 off the circuit board. Well, maybe we'd desolder it, but we remove it. And then we'd stick a 6809 in, but we'd have a little gizmo. It was called a ZIF socket. We'd have a little gizmo that crossed up the wires that needed to be crossed up. We'd stick that in, and then we turned the PET into a 6809 processor instead of a 6502, and then we could write actual software, closer to what we were used to doing. So that worked well. I mentioned heat death. So these computers don't have fans. They run at 1 megahertz clock cycle as opposed to, like 3.5 gigahertz. And the 6809 ran a little bit hotter than the 6502. So these things used to fail regularly because they got too hot. So the way we solved that problem was we bought about 16 cases of that compressed Freon stuff that you could squirt out of a can. It's completely and utterly environmentally unfriendly. And so about every 10 minutes, you'd have to lift the hood up, lather the inside of the machine with about half a can of Freon to cool it down, then you close the lid and you can work for another 10 minutes. Eventually, the engineering co-op students, God bless them, that we had figured out how to make that problem go away. But for a while, we were a significant source of the destruction of the ozone layer emanating from the corner of Philip University. Our group was located off campus. As Eric mentioned in his talk, being away from the math building seemed to have some advantages, and we benefited from the same advantage by locating ourselves, off campus. So, where are we? We know we need to have something. We know that the standard computers that you could go and buy weren't any good. Cost was a factor. The stuff we'd done by, popping a 6809 inside here was encouraging, seemed to be a decent programming model. On the problem that we had, though, and it was Wes Graham that was directing the computer systems group, he was nothing if not thrifty. He noted that, having solved the consumables problem by replacing them with all those Volcker Craig terminals and widget, we've now got rooms full of these terminals, and we really don't want to throw them away, because if you buy a whole bunch of these things as they sit, then you're paying for a monitor that you don't really need because you've already got rooms full of monitors. So the original decision was to say, well, why don't we build ourselves one of these? The Microwatt. This is a 6809 based CPU. It is what we would refer to today as a headless computer. Doesn't have a monitor. We already had rooms full of monitors, so there's a place on the back to plug in a monitor, place for a disk drive if you wanted it. There's also a serial port. So that was the decision. We could leverage the investment that we made in all of these Volcker Craig terminals, building these, using those in the lab. Trouble was, this was building a brand new computer, basically from scratch. Although the computer systems group in those days was a decent sized group of people, we had probably 10 full-time staff and another 10 co-op students, something like that. And we seemed to get a lot done. Part of the zeitgeist of, as others have mentioned this morning, was, well, nobody said you can't do it, so I guess we can do it. We got a little worried that we were actually going to be able to build these things. And Wes, this is another characteristic of Wes. Wes loved setting targets. And the more ludicrous the target sounded, the better he liked it. So he said, well, don't forget, I mean, it's April 1980 from the first time we sort of figured out how to do anything with these. So he said, well, fall of 81, we're going to have rooms full of these things ready to use. So that's a year and a bit away. I mean, this is crazier than a NASA technical schedule. So, you know, work proceeded, and we got a little nervous. And we already knew that we could take one of these things and put a 6809 inside it. So we thought, well, we're going to hedge our bets, and we'll develop something that can go inside a standard PET. Basically, whatever we're putting in here, we'll try and put it inside there. It accelerated the development process because we, you know, 2/3 of the thing was already there. It meant we were buying, you know, computers with monitors, which we didn't really want to do. But on the other hand, it would be embarrassing if we had 900 people show up to take CS180 and they had no computer to use. So we started working on what I referred to as a 6809 enhanced 8032, that's the model of this particular computer. We were going to have to write an operating system from scratch, or an operating environment. Calling it an operating system is a bit of a stretch. We needed to build a collection of programming languages that would be useful in the first and second year courses. We needed to build a development environment that either ran on it, which we would use in the hardware courses, or a development environment that let us develop the stuff remotely and deliver it to the computer. And so we set about doing that. This would be sort of late 1980 with a target of 1981 to have it all up and running. So, key point is that basically these are the same computer. This is what you would call the Headless enterprise version, and this is the consumer package version. This is a thing that Commodore got. We were working with Commodore in these days because they, you know, really wasn't kosher for us to sort of, you know, start taking their computers apart and putting new things inside them. So we had you know, worked with them on the development. They got interested in it. They decided they wanted to build a consumer version, and that was great. We were still charging ahead with building these, and eventually we did get the bugs ironed out, and we built these. And there were rooms full of them that were used principally, I think, in CS250 was where they were, which was a hardware course in those days. One of the important things that we did, and this speaks back to that issue of you know, how to use it in an institutional or a lab setting, is they both came with RS-232 communication standard. That was not what was common in the industry. I think the TRS-80 had RS-232 communication standard. The Apple II, you could buy it for about an $800 option to buy a modem to go in it. Certainly, it was possible to use 5 1/4-inch floppies. Does everybody know what they are? Most people, look around there, most people know what they are. I can pull one out. So a 5 1/4-inch floppy is one of these things that holds a stunning 720 kbytes of memory. Anybody who's got an electronic watch has way more memory in their watch than that thing does. As I said, we could use disks with these systems, and that's the way we'll be looking at it today. But in the lab deployment, we used central storage and a communications protocol. We built one of the other things we had to do besides everything else we had to do was we built a communications protocol to talk between these things and the mainframe, or the front end to the mainframe, the communications front end to the mainframe. HostComm was definitely a protocol of its own. We were, I think it would be fair to say, we were not paying a lot of attention to the other work going on in data communications in that era. That's perhaps hubris, but we said, well, you know, we'll just do it ourselves. There was a talk about a year and a half ago by somebody who was a student here in those days, came to talk on behalf of the museum, and he's actually reverse engineered the HostComm protocol because sadly the source code for all of these things has been lost. So we can't go and find it anymore, but it's a story unto itself. Anyway, so what do we want? We want one computer per person. We want access to the bare machine, to the bare metal for the hardware programming course. We need a variety of high-level languages for use in the computing courses. And in fact, because APL is on that list, APL, the eloquently named app programming language. For those of you keen on trivia, APL was devised initially by somebody by the name of Ken Iverson, who had been an academic at Harvard, I think, spent some time there. And he got seduced by the dark side, went to work for IBM, where he immediately went and implemented the stuff he described in his PhD thesis, which turned out to be APL. For those of you extra keen on trivia, at Convocation 2 weeks ago, the J.W. Graham Medal in Computing and Innovation was given to Vicki Iverson, who is in fact Ken Iverson's granddaughter. So there, now you know. We had a bunch of high-level languages, APL, BASIC, which didn't get used in courses. COBOL and Fortran were the standard. Pascal was this radical up-and-coming thing. Remember the first time that I ran across Pascal was when I was taking a course from Frank Tompa, which was taught as a standard in those days in Algol, but there was this brilliant new radical language that we were welcome to try if we could figure out where we could use it, and that was called Pascal. And then 3 years later, I was writing Pascal compilers left and right. So that sort of satisfied most of the high-level courses. We also built a development system, an assembler language development system for use in CS250. So, just to remind us, what we were trying to accomplish here. We were not trying to compete with the enthusiast, hobbyist market. We were building software packages that were designed for teaching and development, as was completely contrary to convention at the time. These languages were interpreted. They were not compiled. In those days, everybody wanted to compile languages because that's what gave you performance. We said we don't care about performance. We're here for student computing, students who want to run the program until they get it working, then they want to move to the next question on the assignment. We were willing to sacrifice, substantially sacrifice, I should point out, runtime performance in order to get security, error handling and diagnostics. As Don mentioned, you know, a typical thing that happened on a production compiler is if your program blew up, what you ended up with was 700 pages of core dump, which nobody read and immediately went to the recycling bin. You know, that wasn't viewed as an acceptable solution in a student computing lab, so we wanted to focus on the diagnostics. If you did something wrong, the system was supposed to detect that and tell you what you did wrong. One of the goals that we had was to make it a reasonably seamless transition across the various languages. If you were using COBOL in one course, the next term you were using Fortran in a different course, you didn't want to have to relearn the environment, so we had an IDE, integrated development environment, that was common across, well, everything except APL, because APL is magically different. And as I noted, these systems were all designed to be run without having local storage. They were all run off of networking protocol, networking system. That in itself, you got to remember, this is 1980, 81. Ethernet had been described. Bob Metcalf, who's PhD thesis from somewhere in California, I can't remember, Stanford maybe, was 1976, and he described the initial elements of Ethernet. It wasn't commercially available till 1980, 79, 80, where it was $1,000 or more a port, and only available in specific hardware, not available generally where you could, plug it into anything. So the state of the art of networking in those days for commonly available computers anyway was serial communications, 9600 baud, funny old modems. It was not great, but it's what we had. We were very much a group, as a development group, we were very much well, let's solve the problem any way we know how and we'll worry about how to make it better tomorrow. And in a lot of cases, tomorrow never came because we were onto something radically new and different anyway. So that was the goals, substantially different goals than you might find for a commercial product, but that was okay because this Computer Systems Group, CSG in those days, our mandate was to support computing technology and platforms for teaching. Just as an aside, for those of you who are interested in such things, how did we do this development? We wrote it in a local dialect of C called WSL, Waterloo Systems language. Well, there's a whole story behind why we had to do that, and then if somebody asks me the question, I'll tell you, but I'll just leave it at that for the moment. WSL was capable of generating code that ran on everything from 8-bit microprocessors up to IBM mainframes, and in subsequent years, we ran it on DEC VAXs. We had a library that ran under VAX Unix. Software portability was a major topic of interest in computing in those days. In the Department of Computer Science, there was an entire research group, the PORT group, that was dedicated to understanding software portability. A guy by the name of David Cheriton was a product of that. That research group, and in fact, Cheriton and his work was a big influence on those of us particularly those of us fresh out of school at the Computer Systems Group in those days. We had to write a small operating system kernel, which was written in assembler for each target machine, but then the vast majority of the operating systems were written in this high-level language, which was becoming standard 80, 81, 82. 5 years earlier, that would have been considered completely radical, but we were getting to it. We were not at the state where we could actually develop on these systems that we were building, so we had to develop on a larger system. In our case, our lab had our own VM370 IBM mainframe, so we would do most of the development on there or on a PDP-11 45 that we had as a development machine. And then we would do what was known as cross-compiling. You compile it on one machine and say, you're not going to run here, you're going to run over there. And then we would do that compilation and we would move it down to one of these things using our hostcom protocol. We also had to burn EPROMs, burn chips to go inside these because some of the software is resident in firmware. And so we actually had our own chip burning facility, which was connected to a PDP-11. Then, in October 1981, the IBM PC was formally announced. It, of course, had been rumored for months prior to that. And that really spelled the end of us trying to do anything more with these. You know, if the IBM PC doesn't arrive, this is a system which has great utility in an educational environment. It had the potential, to become widely deployed. It never happened. People looked at the IBM PC and said, well, it's IBM. You know, nobody ever got fired for buying IBM was the motto, the mantra in those days. You know, the demand came on us. The computing center here was saying, well, you know, you guys, your Microwatts and your SuperPETs are nice, but really we got to have IBM PCs because that's the thing. And so it kind of strangled the ability for us to do substantial further development with these systems. However, because we were so interested in software portability, not all was lost. We took the software we developed and we retargeted it, ported it to other platforms. We built a version of the Pascal processor that ran on here for the Commodore 64. We, of course, ported them all immediately to the IBM PC because that's, you know, where the future seemed to be. Anybody here in high school in Ontario between about 1985 and 1990 or thereabouts, you may have encountered something called an icon, SEMCOR icon, which was the Ontario government's attempt to standardize computing and curriculum, high school curriculum in the mid-'80s. That didn't work out so well. It had its own little problems. The Wikipedia page on the SEMCOR icon is worth reading if you're particularly interested in that. The most interesting thing that happened is the operating system that ran on the icon was in fact QNX, the same QNX that got bought by BlackBerry a few years ago, which is now in 3 out of every 4 cars driving down the road. Their electronics are all running on a QNX platform, something like that. So that's about everything I have to say. We got enough time for a demo, so that's good. We'll take questions and comments as we're doing the demo. And if you're interested, these slides will be made available if you're interested. But there's a lot of resources out on the internet for this kind of work. Okay, if you would, we're going to, as somebody said at the beginning, there's no HDMI out on one of these things. I should point out, you know, this is 40-year-old technology, and the fact that it works at all is somewhat remarkable. So in order for you to see what's going on here, we've got the video camera. All right, how are we doing? Are we good? I just have to watch out. Somebody yell at me if I keep, you know, doing this. So what we've got to start with, this is the sort of standard unmodified Commodore PET. I thought I would just show you the context here, what we're dealing with. 31,000 bytes of memory. It's just stunning compared to what was available in the as a standard in the PET, or excuse me, in the TRS-80 or the Apple II, which was 4K of memory. This was just like nirvana. So, and you have to bear with me as I try and type here. Whoops. Some of the keys on a 40-year-old keyboard are a little sticky. So that is how you load a program off the disk. This is a brilliant six-line standard basic kind of program. You know, it runs, it's just fabulous. That's the kind of operating environment that was considered state-of-the-art in the days. So, you know, as I mentioned, the first thing we did with these things was said, well, that basic sucks. You'll notice the go-to statement, the funny-looking ifs. I mean, that's just the way you had to do things in those days. And we said, well, that's no good from a pedagogical perspective. So we said, we can make that better. Whoops. There we go. Yeah, it's always a little dicey. Every time I turn this thing on, I'm just never sure if it's going to work. So we found a way to take the existing basic interpreter and tweak it to make it better. You'll notice my ISO standard compliant date there, although I wasn't too big on 4 digits in the year, but whoops. Sorry, I got to refer to my cheat sheet here. So this is the sort of equivalent program in our structured basic. Looks more like a sort of program. It's got an if with an else. I mean, that was a radical departure. And I mean, an if with an else statement, it's it's too weird. The other thing that's unbelievably weird is you'll notice we actually get to indent statements. The standard at the time was, white space. Well, that's just using memory. We won't bother with that. So if you think back a second to the program I showed you, nothing was indented because, why would you want to waste all that memory on indentation? I mean, in today's world, Python programmers would just be going insane. What do you mean I can't indent anything? I mean, their heads would explode or something. Anyway, so this was one of the things, and we added this standard sort of set of structured programming statements, loops, whiles. There was a for statement, but it was kind of primitive. So we just kind of, we actually let you define subroutines with names. And once again, it's a brilliant piece of software. It actually runs. But that was the kind of environment we were coming from. That's what the standard state-of-the-art of desktop computing was, 1980. So we said, well, that's no good. In the lab, we want something better. So we did all the development that I've discussed. And you can't see it, but there's a little switch on the side here. One of them says 6502. That's the standard processor that goes in here. And the other one says 6809, which is the add-in board that we created. So you flip the little switch, and you load an entirely separate set of ROMs, an entirely separate set of firmware. This is the stuff that we created. I should point out the name Waterloo Microsystems. We sort of grabbed that name because it sounded like a good name. About a year later, a company in town that I think was founded by Mike Malcolm, Mike Malcolm was involved with, copyrighted the name or trademarked the name Waterloo Microsystems. It was kind of confusing. We got in trouble. Anyway, you fire it up, this is what you got, this is in the firmware. You get to pick what programming language you'd like to have. We'll do a little demo with Pascal. Now, you'll see that it's loading. It's loading off this disk drive. Remember, 720K bytes, it transfers about, 5K bytes a second or something like that. No, it's less than that, probably 500 bytes a second. So this is what the students were faced with. Now, this is going to go on for about 40 seconds, so I got to fill time here. This was not what upset people. I mean, this was okay, right? Because compared to loading off of a cassette tape, that was about 10 times the speed. So you load that, you get the integrated development environment. We can get whoops. I still can't type any better than I could in 1981. Get ourselves a canonical little hello world program in Pascal. And once again, you can run that, and it runs. And that was radical. What do you mean it's not basic? It's Pascal. Oh my God, my head's going to explode. How did you do that? We had Pascal. We can say bye. We can do Fortran. This will once again take a second or two to load. The version of Fortran that we used, of course, was heavily influenced by Watt 4, Watt 5, which was developed, out of the same set of people, or the previous group were sort of the immediate descendants of the Watt 4, Watt 5 development team. How are we doing for time? I guess we're
running very short.
Yeah, okay.
I just want to point out too, we will have the emulators that you can play with this in MC3011, and instructions how to load it on your own Linux box.
Well, if we're running out of time, what I'm going to do is I'll just say bye to this, because what I do want to do is show you APL, since I promised I would show you APL. APL is a language that was developed, as I say, as a mathematical formulation language. Worked on scalars, vectors, tensors. It came with a whole whack of primitive operators to do things to any of those class of objects. It was notorious because in order to get that set of operators, as Iverson specified the language, she used a completely different character set. So if you have a chance to go over to the lab, or you can come down in a minute and look, you'll see that the key labels, or there's an alternate set of key labels across the front of all of the keys, representing the APL character set. So in addition to everything else that we were doing in the 1980-1981 timeframe, we had to figure out how to build our own character sets and replace the character generator chips inside one of these things as well. So just to give you a flavor of APL, APL is a sort of an operating environment language. You don't write programs as much as you just type expressions and they do things. So if you tell it the number 42, it gives you the number 42. If you say 2 plus 3, it tells you 5. You can do fun things like iota 10, whoops, not 110, thank you, iota 10. Iota is one of those funny little Greek letter primitive operators that generates a vector of integers from 1 to whatever number you specified. So iota 10 generates you a vector of that. You can, of course, assign that to a variable. So let's do that one again. Type V, you get that. You get to do what were called reductions. Any operator that you have, like adding 2 plus 3 is 5, you can apply to a vector. So that would be done by going +/V, which adds up all of the numbers in that vector. If we have A gets, I should really buy myself a new pair of glasses, shouldn't I? A gets 55, B gets 66, 66. All right, 65, I'm not gonna argue. You can do things like A floor B, that will choose the lesser, and of course, that would be no good if there weren't a ceiling operator, A choose B, and it goes on and on. I mean, there's 20 different operators that are funny looking Greek characters, and they all do something magical. Unfortunately, as I'm wont to do, I've talked too long, so we won't get to extend this demo, but I'm happy to talk to people later if they're interested. Anyway, that's what I have to say.